Welcome to the session on S390, stack tracing using frame pointer, backchain, and SFrame. And before I start, I would like to clarify a little bit this S390 terminology. Commonly, S390 is used to distinguish our architecture from the others, such as x86 and Power. And more specifically, S390 refers to the 32-bit ELF ABI. And S390...
31.
Yeah, but we dislike to call it like that because that confuses people even further. And S390X refers to the 64-bit ELF ABI. And throughout this presentation, S390 and S390X are used interchangeably because 32 bits or 31 bits are getting less and less relevant. So let's start with stack tracing, what this means in the context of the session. And for that, let's have a look at what is a stack trace. That's a snapshot of the sequence of function calls that a program went through up to a certain point. And usually that's the current instruction pointer, followed by the sequence of return addresses. And here on the right is an example from perf with option call graph. And so on the top, you have the instruction pointer, and then followed by the return addresses. Here it's annotated with additional information like the function name and offset within the file name. And due to dwarf, there are even inline functions. Other examples are in Glibc, the backtrace function, in GDB if you use the bt command. And usually, as we've seen, that's annotated with all kinds of interesting information. So what's then stack tracing? That is this process of starting from the current program instruction pointer to record that and then somehow determine the sequence of return addresses until reaching a so-called outermost frame, such as start, where there is no caller. And that is sometimes or usually identified by something like the return address is 0. And the instruction pointer relates to the topmost frame and the last return address to this outermost frame. This is a very high-level pseudocode for such a stack tracer, and we will see more of them. I just want to point out, so we start with recording the instruction pointer, and then starting with the return address, we determine, or starting with the current instruction pointer, we determine the return addresses, and as long as they are valid, we record them and repeat. So why am I interested about stack tracing, especially of user space on S390? And for that, you have to know that stack tracing using frame pointer, which we will have a closer look soon, is not supported on S390, while it is on most other architectures. And in context of profiling, for example, using perf, it means the only available option is this call graph dwarf, which does stack dump sampling. So by default, 8 kilobytes of the stack are dumped away. And this generates a fairly large amount of data, and that can lead to lost samples if perf cannot keep up writing this away. And due to the fact that it only records a part of the stack, like the 8K, it causes incomplete stack traces if the stack size used is larger. To compare this against the other methods, in this case, the stack tracing using the dwarf CFI happens during post-processing, so the performance of the stack tracer is, let's say, secondary. And when we compare that against another option available on the other architectures, this call graph with frame pointer, which is not yet supported on S390, There, the stack tracing is performed at runtime, so the performance of the stack tracer is important. And it records only the instruction pointer and return addresses, which is a small amount of data, and ideally the stack trace is then more reliable because, for instance, we can generate a complete stack trace if the stack size used is large. So let's have a look at stack tracing using frame pointer. And for that, let's have a look at what is a frame pointer. And for that, we need to differentiate it from the stack pointer. So stack pointer is the register that always points at the top of the stack, and that changes during the function execution because of static stack allocation, dynamic stack allocation, pushing, popping values. And in contrast, the frame pointer is a register that points at a fixed reference point of the current frame. So it's constant after setup during the function execution, and it eases access to function arguments, in case of s390, the register safe area, local variables on the stack, especially after dynamic stack allocation, because all those offsets from the frame pointer are then constant. It is set up by the compiler prior to dynamic stack allocation. It can also be forced using compiler options. So there is this generic fno-omit-frame-pointer and the architecture-specific mno-omit-leaf-frame-pointer that I think is implemented on x86 and ARM and possibly others. And usually it's set up early in the function prologue. So how does stack tracing using frame pointer work? There are some pre-requirements that must be guaranteed by the architecture and or ABI. So we need a designated frame pointer register. So for startup, we need to know which register we start the stack trace with, and also which register do we restore from the stack. We need fixed stack safe slot offsets from the frame pointer for the caller's frame pointer and the return address. And the frame pointer must always be set up, and the frame pointer and return address must always be saved to the stack in the function prologue, which can be achieved using said compiler options. And last, we need an indication when reaching this outermost frame. For instance, that can be that the frame pointer and or return address are 0. So if we have a look at pseudocode for such a stack tracer, we again start with recording the instruction pointer, and then beginning from the current frame pointer register value, as long as the frame pointer is valid, we retrieve the saved return address and the saved caller's frame pointer from the stack at those fixed offset locations. And as long, for instance, depending on this indication for the outermost frame, as the return address is valid, we record that and just repeat. Note, though, that this is not perfect. So the frame pointer either points to the caller's or the own stack frame. So at function entry, the frame pointer register has the value of the caller, and a stack tracer at that point would then skip the caller, so it would record the caller's caller. And only after the frame pointer has been set up in the prologue, it would correctly record the caller. There are other particular issues, but this is the one that is probably valid for most architectures. So why is stack tracing using frame pointer virtually impossible on s390? And that is because our ABI does not designate a frame pointer register. So the compiler is free to choose any register as frame pointer. Does this mean we can't really do this? No, because in practice, GCC and Clang use register 11. And so as of late, we have adjusted our ABI to designate register 11 as preferred frame pointer register. Note, though, that there are some edge cases where the compiler still uses other registers. For instance, GCC may use the return address register R14 in the stack clash protector as frame pointer, but let's say for most cases, we can still use frame pointer. We could still use frame pointer. So the next issue is that our ABI does not specify a fixed stack register save area layout. So there are no fixed offsets. Does that mean we can't use frame pointer? No, because again, in practice, GCC and Clang adhere to the sample layout from the ABI, so there are fixed offsets. But then our ABI does not specify when to set up the frame pointer. And GCC and Clang set up the frame pointer as late as possible, and that is after static stack allocation. The background is several instructions only use an unsigned displacement. And to be able to address the static stack contents, local variables, using the frame pointer as base, it must be set up after static stack allocation. And this means the frame pointer and return address stack save slots from the frame pointer are unknown, at least without any additional information like dwarf or SFrame. And that's basically why SFrame, when we come to it, is interesting for us. Of course, we could possibly resolve this by having fno-omit-frame-pointer do the right thing, that is set up the frame pointer immediately after saving the registers. But this would require thorough investigation of the performance implications. And currently, we consider this wasted effort as we see that Linux distributions appear to move away from no-omit-frame-pointer. And in essence, this means on S390, you should avoid using fno-omit-frame-pointer because it only adds unnecessary overhead with no benefits. So it can't be used for frame pointer-based stack tracing. It unnecessarily sets up a frame pointer register even if not required. And then it consumes a register that would otherwise be useful for other purposes. So let's have a look at an S390 specific alternative. That is the backchain. There is something similar in power, but it works a bit different. So I will be focusing on the S390 implementation. This can be enabled using the, yes?
Is there only one stack layout or were there multiple in S390?
There is a kernel
save
layout.
area. The save area layout, is there one or multiple depending on?
So there is this layout for user space. That is what the left one is the one that the ABI specifies for user space. The right one, as it says, is this usage example. And as I mentioned, the compilers currently adhere to that. There is a different layout for kernel. So when the kernel compiles with m-packed stack to enable packed stack, then the backchain field moves to the top, and like the stack frames can then overlap.
So even if then the frame pointer method is used, there will still be ambiguity.
Excuse me, can you?
So even if we were to use the frame pointer, there will still be ambiguity, right? Because the return address, even if you do identify this register save area, the return address goes at different location in the register save area.
I think this is different though. He's talking, the previous page
Yeah.
was talking about how you do it with frame pointer.
Yeah,
This is talking about using a backchain,
I see.
where the return address is saved on the stack, so not using the frame pointer. So this version doesn't use the frame pointer.
So I think what you are asking is this part. So although that the ABI does not specify at what offsets of the register save area particular registers should be saved, the compiler do it as shown in the sample, and the sample has like specified places, offsets. But it's not that the ABI mandates the compiler to do this. It's just the current compiler implementations do it as the sample. And so, yeah.
It's the preferred layout.
Yeah, it's a right. So let's come to backchain. It can be enabled using this mBackchain, and this adds a caller-maintained backchain field to the caller-provided stack frame. It's at the top of the stack frame in user space, and just as a side note, as I will be only focusing on user space, in the kernel stack frame, it's at the bottom of the stack frame. There is this
stack frame always the same size? Because the register save area can vary depending on how many registers you save.
So it's a caller provided, so the caller provides a function with 160 bytes of register save area space.
Always?
Always.
Okay.
That's required. And note that this has the same issues as with frame pointers. So the backchain either points at the caller's or own stack frame. So there is the same issue that sometimes stack tracer would record the caller's caller instead of the caller. And so you can think of this as a frame pointer on stack. And a backchain value of 0 indicates that an outermost frame is reached. The compiler option also guarantees that the prolog saves the return address and stack pointer registers into the register save area into those slots that correspond to the usage example. So there it actually specifies which offsets, which means there is a heuristic to tell whether the backchain is kind of valid. If the backchain value has the same value as the stack pointer saved in the stack frame pointed to by the backchain, then it seems good. And if we look at pseudocode, then as always, we start with saving the instruction pointer, and then with the initial backchain, as long as the backchain is valid, we retrieve the return address and stack pointer from the stack at the constant or the fixed offsets. We can check this heuristic, and then if it's valid, we save the return address and we repeat with the next backchain. So let's have a quick look at several issues with the backchain. So as already mentioned, in the at function entry, the stack pointer points at the caller provided stack frame and the backchain points at the caller stack frame. The return address is in a register. And so the stack tracer, as explained, skips the caller. And there is no heuristic to say, oh, the stack tracer should better use the return address from the register. After saving the registers, it's the same issue, and there is also no heuristic to say now we should retrieve it from the stack save slot. But then it gets worse. So during stack allocation, whether it's static or dynamic allocation, we allocate the static stack space plus a register save area for calling a function which has now an uninitialized backchain field. And this means that a stack tracer fails at large. So either it cannot follow the backchain at all, or it now follows a stale backchain. And due to the fact that function instructions can be intermingled with the prolog, this increases the chance for a stack tracer to hit this issue. So only after the backchain field has been written, a stack tracer would get a correct stack trace. The same issue then repeats if dynamic stack allocation occurs, with the same issue that instructions get intermingled to increase the chance. But that's not all. So the Linux Kernel VDSO on S390 allocates a non-standard stack frame for legacy Glibc compatibility. So old Glibc called VDSO without providing a standard stack frame. And this means a stack tracer needs special handling for this non-standard stack frame in VDSO, as can be seen in the kernel stack tracer. And what basically prevents us from using backchain is that no major distribution compiles user space with mbackchain.
Ubuntu does now.
Excuse me?
Ubuntu does now.
Oh, okay. I didn't know. So
Well, maybe
Thank
you should talk internally.
yeah, but I mean, given all those issues where the stack tracing fails,
For the wrong reasons. As you hear, it doesn't work anyway.
I don't say it doesn't work. It has issues.
It doesn't reliable. It doesn't reliable.
Yeah. Okay, then let's come to stack tracing using SFrame. And first of all, what is SFrame? So SFrame stands for simple frame stack trace information. It's generated from dwarf CFI, the call frame information, or those CFI directives in the assembler, more precise. And it basically tracks the information required to restore the CFA, the canonical frame address, the frame pointer, and return address. And more specific, it tracks the CFA base register. Currently, SFrame only supports the stack pointer or frame pointer register as CFA base register, and the CFA base offset from CFA offset from CFA base register. And then optional, it can track the return address stack save slot offset from CFA. As an alternative, it can also use a fixed return address offset, which is used on x86. And the same, it can optionally track the frame pointer stack save slot offset. There is also this alternative fixed offset, which I believe is not used right now on any architecture. And for both this return address stack save slot and frame pointer stack save slot tracking, if there is no information, then the return address or frame pointer remain unchanged, which we'll see soon in the pseudocode. For the stack pointer, SFrame relies on the definition of the CFA. And so dwarf version 5 states, typically the CFA is defined to be the value of the stack pointer at the call site in the previous frame, which boils down to the stack pointer equals CFA, which is valid for most architectures.
It says typically, so you can define whatever you want. What? It says typically, you can define whatever you want in your ABI. Something else makes sense for your ABI. The CFA can be whatever makes sense for you.
Yeah, but my understanding is that most ABIs follow this. That's why I kept this typically, because we will come to what s390 does. So how does SFrame stack trace information layout look like? There is an SFrame header, which has information about the SFrame section. It has this fixed return address and frame pointer offsets, those optional ones. And it can also have an architecture-dependent extension, an optional one, which I believe also no architecture currently makes use of. Then there are the SFrame FDEs, the function descriptor entries. They contain information on functions such as the start address, size, and pointers to the SFrame FREs we will see next. Those frame descriptor entries are fixed size and sorted on PC, which means binary search can be performed, which is fast. And then there are those SFrame FREs, the frame row entries. They contain information how to restore the CFA, frame pointer, and return address for a range of PCs of a function. And they are of variable size, sorted on PC, meaning linear search must be used. To compare dwarf CFI against SFrame, so you get a rough idea. So on the left, we have dwarf CFI in this instruction listing representation for a sample function. This roughly represents how dwarf is also saved in the format. As this is not very friendly to read, there is this tabular representation. And So for the location in the function, you have the information how to restore the CFA, various registers. And SFrame is similar to this tabular format, and it contains only the information required to restore the CFA, the frame pointer. This is register 11 on s390, the preferred frame pointer, and the return address. So how does stack tracing using SFrame work? In this pseudocode, we again start with recording the current instruction pointer. And then for recording the sequence of return addresses, we need some setup. So first of all, we look up the frame row entry that is applicable to the current instruction pointer. We initialize the stack pointer and frame pointer to the stack pointer and frame pointer register contents. And if the architecture has a return address register, we do the same with the return address. And then we restore the CFA, which is either stack pointer or frame pointer based. The frame row entry has this information, what to use, and we simply add the CFA offset. Next, we restore the stack pointer using this CFA definition, which is, again, only valid for most architectures. Then we restore the frame pointer, either using this fixed frame pointer offset from the SFrame header, or, if available, using this tracked frame pointer offset. And here you see if there is no offset, then the frame pointer value just remains unchanged. Repeat the same with the return address. And then as long as the return address is valid, we record that, and then we repeat by doing the frame row entry lookup for the return address. Okay, so how does this work for s390? First of all, the SFrame return address tracking requires a designated return address register, which our ABI designates. Then the SFrame CFA and frame pointer tracking requires a designated frame pointer register. And here you remember s390 does not designate one, but as the compilers in practice use a fixed register, we can use that. There are still those edge cases where this won't work, but still it's better than nothing. Then SFrame relies on the CFA definition to restore the stack pointer. That, remember this assumption, stack pointer equal CFA, and doesn't work for s390 because our ABI defines the CFA to be the stack pointer at call site plus 160. And I've resolved that using an s390x specific stack pointer value offset from CFA. Then SFrame cannot represent the frame pointer or return address saved in another register. And our compilers may save those in a floating point register, for instance, when in a leave function. And so I've implemented a s390x specific extension to represent the frame pointer or return address saved in another register, which is only valid for the topmost frame. Our next SFrame cannot represent the frame pointer without the return address saved. Our compilers happen to do this. So either they save the frame pointer without saving the return address, or when restoring, they restore the return address prior to the frame pointer. And again, I've implemented a s390x specific extension to represent this in SFrame. And last, those SFrame frame row entries, they are accompanied by those 1, 2, 3 offsets for the CFA return address and frame pointer. And they can be either 8, 16, or 32-bit in size. And the largest of those 3 offsets determines the size for all 3 of them, or 1, 2, 3 of them. And as our CFA definition how to say, due to our CFA definition, the minimum CFA offset is 160, and this does not fit in 8-bit. We assigned 8-bit. We would never use those small offsets. And so I've implemented an S390 specific CFA offset encoding in SFrame. Let's have a short look at that. So for the S390X specific SFrame stack pointer value offset from CFA, that's pretty obvious. So there is just a stack pointer value offset of -160 that needs to be used, and the stack tracer needs to use this specific rule for S390 to restore the stack pointer. And effectively, in a stack tracer implementation, we use a generic stack pointer value offset of 0. We assume that works for all other architectures. And then for S390X, we override this with our specific one. Then for this extension to represent the frame pointer return address register safe area, frame pointer return address saved in a register, the solution is to encode the dwarf register number as a offset. And this works as follows. So if the least significant bit is 0, it's a stack slot offset. And that is because the ABI guarantees that those offsets are 8-byte aligned. So the least significant bit is always 0. And this is the case because both the stack pointer is mandated to be 8-byte aligned, as well as integers and 64-bit integers and pointers are also 8-byte aligned. So the stack safe slot offsets are aligned. And if the least significant bit is 1, then it's a dwarf register number shifted to the left by 1 and the least significant bit set. And for the stack tracer, this is only valid for the topmost frame because otherwise the stack tracer doesn't have access to arbitrary register contents. The helper macros are just for the curious that want to look up in the code. So next is this S390X specific SFrame extension to represent the frame pointer without return address saved. Let's have a quick look why this is an issue. So the SFrame frame row entries are accompanied by those 1, 2, 3 offsets. And the mapping is as follows. If there is 1 offset, then this is the CFA offset. If there are 2 offsets, it's the CFA and the return address offsets. And if there are 3 offsets, it's a CFA, return address, and frame pointer offset. And this means there is no representation for 2 offsets where one is the CFA and the other the frame pointer. And the simple solution is for S390 to use an invalid return address offset value of 0 as a padding offset, so to use 3 offsets. And the stack tracer treats this as if no offset was present. Then let's have a look at the encoding of the CFA offset. So as already mentioned, those 1, 2, 3 offsets, the largest one determines the size. Due to the CFA definition, it doesn't fit the 8-byte offsets. And to make or to enable the use of those signed 8-bit offsets, we adjust the CFA offset by -160. And since we are already now doing something special for S390, we additionally scale it down by 8 to further improve the use of 8-bit offsets. And that is possible because our ABI guarantees the stack pointer and the CFA to be 8-byte aligned. Okay, so what's the status of SFrame on S390 right now? So what is already available are those SFrame version 2 or version 2.5, how you used to call it now, format enhancements for S390. So they are documented in the SFrame specification. And starting with Binutils 2.45, the GNU assembler with option GSFrame generates SFrame from CFI directives on S390. And the GNU linker also generates SFrame for the PLT section and is capable of merging the SFrame sections. And that is like common code, GNU object dump and readelf with option SFrame enabled to format the SFrame information. So from a tool chain perspective, there is everything available to now generate ELF binaries with SFrame and to inspect the contents. What is work in progress? Right now I'm working on an SFrame version 2 enhancement to represent CFI undefined for the return address. This is used in Dwarf as indication for an outermost frame. There is a patch series out there that I expect soon to get reviewed and hopefully committed. And it will represent this return address undefined as an SFrame frame row entry without any offsets. Then I'm working on adding support in Glibc backtrace to use SFrame on s390. Again, there's an RFC patch series already out for that. It depends on work from Claudio Sisulescu from Oracle, who has enabled Glibc backtrace to use SFrame and added the x86 and ARM architecture support for that. For s390, this additionally depends on this SFrame to represent CFI undefined as indication for the outermost frame, as our ABI does not specify any indication for such an outermost frame. So we cannot rely like on X and ARM on things like the frame pointer and or return address are 0. So we need this additional information. And last, I'm working on adding support in the Linux kernel for stack tracing of user space using SFrame on s390. There is also an RFC patch series out, and this depends on the tremendous work by Josh Poimbeuf from Red Hat, and which is now continued by Stephen Rosset from Google, and there are others that have added stuff, so that's not just those two, but Steve is driving this now mostly.
Unfortunately.
And it's like a whole series of series. So there is a patch series that adds a deferred unwinding infrastructure for user space to the kernel that is required because for the kernel to access the SFrame section contents, there can be page faults, and not all kernel contexts can support that. Then there is support in perf for this unwinding infrastructure and the perf tools. And finally, there is a patch series that implements SFrame handling in this deferred unwind infrastructure. And on top of that, the s390 support it builds upon. At the end of the session, I will show you some preliminary results. So for the future, for sure, LLVM needs to support to generate SFrame, not only on s390, but as far as I know, there's somebody working in general on implementing that, but we might have to have a look at like, did all those s390X specific things get integrated? And then Indu will have a talk about SFrame after this session, where she will also go into the details of plans for SFrame version 3. And one thing is it's planned to be able to represent a non-frame pointer stack pointer based CFA base register only for topmost frames to resolve some x86 issue. And I strongly assume that should resolve this issue with, for instance, the return address register R14 being used as frame pointer in the GCC stack clash protector on our architecture, as well as the stack clash protector is only active in the topmost frame. So to give you an idea of the results, so with this work in progress patch series for the kernel, I get smaller perf data, so that the data size is greatly reduced. So on the top, you see the stack dump sampling using callgraph dwarf, and at the bottom using SFrame, and the data file size reduces from 67 megabytes to around 2.5 megabytes. And then also the sampling rate is is a lot higher. So at the top, we again have the stack dump sampling, at the bottom SFrame, and I'm using an insane sampling rate that is near the maximum possible. So you see for the stack dump sampling, there are lost samples. You have a huge data size. And for SFrame, we have no lost samples, and the sample count is a lot higher. So we have those like 283,000 compared to those 82,000 samples. And the file size, again, is much smaller. So that's what I wanted to share with you. Are there any questions?
What about that support in LLD?
I have to defer to Indu. I mean,
So they are working on it. SFrame support is ongoing. Yeah, so I've seen patches where they've added support for dumping SFrame and also generating SFrame in the assembler side. They are working on the linker patches too. So SFrame support in LLD should come soon. Timeline-wise, I don't know, but it's in the works, yes. For Mold 2, we had filed a request for, adding SFrame support. I don't think anybody has taken up on that PR yet. That's all for that's for the other two, compilers, LLD and Mold. But what else is there? I think for now, maybe these two.
yeah, let me add that the linker to merge SFrame, there is nothing SFrame specific, nothing s390 specific. What is s390 specific in the linker is generating SFrame for the PLT, because the PLT is synthesized. So yeah.
So the assembler option you added there, or talked about, to create the SFrame data, does that remove the dwarf data? So so they're both there. So user level debugging with GDB, if I'm a user, I can go off and do that.
Yeah,
okay, it's just extra.
It's extra, yeah.
Okay.
And as far as I know, some distribution went ahead and added a Binutils configure option, so that the assembler would generate SFrame by default. Because if you want to build the whole user space using SFrame, for them that's the easier approach than to inject this GSFrame option everywhere.
Yeah, that's upstream now. So it's an upstream option. So if Binutils supports a configure time flag where you would say enable default SFrame, so then the assembler generated will by default emit an SFrame anytime it assembles something. But yeah, we need to be. Yes, master, not yet released. It's master. It will be an option in 246. And what this option also does, by the way, is it disables any warnings or errors. So for example, if you invoke an assembler on a target which does not support SFrame. So SFrame is supported on AMD 64 ABI. But if you say something like, I want on x86 or 32-bit architecture, then it does error out saying, I don't support SFrame for it. So, yeah.
Okay, then thank you.